So this is lecture 2.5. In this lecture, we are going to talk about time domain specifications, right? Time domain, time response specifications of second order system. So just like for the case of first order systems, we define certain quantities like the time constant, the rise time, and the settling time. In a similar way, we would also like to define certain quantities for second order response. A brief overview of the second order response that we have seen till now. So we have seen step responses for second order systems for different cases of damping and damping ratio. We have taken the second order system to be a 1 without a 0. So it will be k omega n square. We have written it at k omega n square divided by s square plus twice zeta omega n s plus omega n square. So this is our second order system. And we have analyzed the response to step input Rs is equal to 1 by s. And we have seen that for stable second order systems, that is the case in which the poles of the system are on the left half plane, we'll have four types of responses for different values of zeta. Undamped response for zeta equal to 1, and underdamped response for zeta between 0 and 1, a critically damped response for zeta equal to 1, and an overdamped response for zeta greater than 1. Here the y-axis has been normalized. So basically you see a response as a function of as Ct divided by the gain k. So assuming that the gain k here is 1, that is why your responses are all settling down. Normally they settle down at k, but here they're all settling down at the value equal to 1. And the undamped response has a peak equal to twice of the steady state value. Okay, so now we have also seen that we can very easily quickly see what is the response, we see what we would easily expect what is the response if we know the pole locations. And the pole locations are obtained by putting the denominator polynomial s square plus twice zeta omega n s plus omega n square, equating this denominator polynomial to 0, find out the pole locations of the transfer function gs, right? And if the poles are purely imaginary, right, in the case zeta is equal to 0, they'll be at plus j omega n and minus j omega n, then you'll have an undamped response. If the poles have imaginary components, but they also have some real part, the real part being equal to minus zeta omega n and the imaginary part being equal to, so the poles in this case would be minus zeta omega n plus minus j omega n under root of 1 minus zeta square, which is also called omega d, the damped natural frequency. So minus zeta omega n plus minus j omega d. Then the response would be underdamped. There would be oscillations. The frequency of the oscillations would be determined by the imaginary component, and the exponential decay would be determined by the real part, right? That minus zeta omega n. If the poles don't have any imaginary component, in the case zeta is equal to 1, wherein this can be written as s plus zeta omega n whole square, then this would be the s plane. The pole locations would be at minus zeta omega n, and in this case, since zeta is equal to 1, the poles would be at plus minus omega n, and the response would be critically damped. There would be no imaginary component. And similarly, you have an overdamped response in case the poles are real and unequal, and the poles are given by minus zeta omega n plus omega n. So this is minus zeta omega n plus minus omega n under root of zeta square minus 1. So in this case, zeta is greater than 1, and the poles would be real, and the response would be overdamped. It would be slow, right? So So the pole locations will tell us what kind of response we'll have. And even in the case, so we see that the underdamped response is the richest of the responses. Richest in the sense that it is exhibiting most features, it is exhibiting an overshoot, it is exhibiting decaying oscillations, it is exhibiting some time taken to settle down to after oscillating to the steady state value, and it is displaying richness in the sense also that if you change the damping ratio, you get different kinds of the the responses in terms of speed and overshoot, right? So if you take a second order underdamped system and try to see it more closely, you will see that for different values of zeta, which would have to lie between 0 and 1, you expect that for smaller values of zeta, you have more overshoot and a faster response and more oscillations, which is clear from this figure. And for bigger values of zeta closer to 1, you have lesser oscillations and less overshoot and quickly settling down to the final value, right? But of course, the system would become slower, right? So this is very clear from this figure. Let's slightly magnify this. You can see that for different values of zeta, the response of the system, the underdamped response of the system changes as the value of zeta changes. But overall, the response has a nature which can be described as similar, right? So now let us take this standard second order response and try to see whether we can, give it define certain things dependent on the response. And please remember that we are taking the second order underdamped response because it is the richest response. It is exhibiting many characteristics, right? So let us, for example, see one very simple thing, two things that we have already defined with respect to first order systems. One was the rise time. If you remember, we defined it as the time taken to reach from 10% to 90% of the final value. So we can also apply the same definition here and try to see what is the rise time. So if we have the final value being called C final here in this graph, the final value at which the second order step response settles down, we see the time taken to rise from 10% of the final value, that is 0.1 C final, to the time taken to rise to 90% of the final value, which is 0.9 C final. And this time that we have in between, we call this time the rise time, right? In a similar way, we can define the other other important parameter which we defined earlier, which was the settling time, which was the time taken to oscillate or settle down between plus minus 2% of the final value. So if you have this final value as C final, and you are oscillating between minus 2%, that is minus 0.9 C final, to plus 2%, which is 1.02 times C final, when you finally start oscillating between these two values, right, you don't leave this band. That is the time which will be called the settling time. So it will be assumed that you have, for all practical purposes, settled down, right? So this is why you have this settling time here. So these two definitions we straight away take from the earlier definition of first order systems, time domain specifications of first order systems. Now you can define one more quantity here, which is called the peak time, and which is the time required to reach the first or maximum peak. So the time required to reach the first peak or the maximum peak is called the peak time. So these are the three important specifications as far as the time is concerned. So let me repeat: the rise time, the settling time, where we're talking about plus minus 2%, settling down within plus minus 2% of C final, right? And the third one is the peak time, which is the time taken to reach the maximum value. So the peak value in this case is here, and this is your settling time, which is very clear from the figure, the time taken to reach the peak here. Now, you can also see what is the overshoot, how much are you overshooting, right? The final value. So this is your final value here, this is your C final, and this is the amount of overshoot that you have. So this is your overshoot, right? And this overshoot you can express as a percent overshoot. So if you express it as percent overshoot, which is generally written like this, it is expressed as a percentage of C final. So for example, your C max, if your C max is say 1.1 times C final, you say that you have a 10% overshoot. So you are overshooting the C final, the final value at which you're settling by 10%, and you're going up to 1.1, right? So these are four important parameters of second order systems, which basically define the performance of second order systems, right? So let us see whether we have something else here on the slide. Okay, now I have already discussed this in my last lecture. If you see the pole locations, pole plot for an underdamped second order system, you see that it is minus zeta omega n plus minus j omega n under root of 1 minus zeta square. It is very helpful to remember these pole locations. So this is minus zeta omega n plus minus j omega d. And you can see that you can draw a number of conclusions from the pole zero plot. One is that your y-intercept is omega d and j omega d and minus j omega d here, and your x coordinate here is minus zeta omega n. And if you actually look at this in terms of the coordinates, the amplitude and argument of the complex number, because these are complex numbers, and if instead of looking at in terms of Cartesian coordinates, you look in terms of polar coordinates, then this can be this distance from the zero is equal to omega n, and you can find that out by just taking the square of the imaginary part, the square of the real part, adding them up, right? Squaring them up and adding them up, and you can see that if you do that, zeta omega n whole square plus omega n under root of 1 minus zeta whole square, which is the amplitude, the r of the complex number in the polar coordinates r theta. You see that this r is equal to zeta square omega n square plus omega n square 1 minus zeta square. This zeta square omega n square, this zeta square omega n square cancels out, and you get, this is r square, you get r is equal to omega n, right? You can also find the value of the angle theta. Theta is going to be tan inverse the y-intercept, which is omega n under root of 1 minus zeta square, divided by x-intercept, which is zeta omega n, right? So your angle theta is tan inverse 1 minus zeta square under root by zeta, right? So your theta, this theta is a function of only zeta, right? And your r is a function of the undamped natural frequency, and the theta is a function of only the damping ratio. So basically, why I'm telling you this is that if you keep zeta constant, right? If you keep zeta constant, and you change omega n, then you'll be basically moving in this line, in this straight line, right? And if you keep omega n constant, if you keep omega n, suppose you're changing the pole locations and you keep omega n constant, you change zeta, then you'll be basically changing the angle. So you'll be moving in a circle. So you'll be moving in a circle like this. Right? So this is an important concept which will be useful later on. So so basically, this is not a point of discussion today. So basically, we have seen now four quantities which describe the. So here it is given slightly, but I'll explain this once we draw the analytical. We write down the analytical expressions for four quantities. So these are the four quantities that we have seen, and their definitions we have seen: rise time, settling time, percent overshoot, and the peak time. Now our next step would be to find precise analytical expressions for these four quantities.